Hello, my name is Reid Haigler, and the title of my presentation today is Whisker Occurrence. I participated in the summer 2020 SE Embry program at Presbyterian College, and my research advisor was Dr. Whisker. So here's an outline of my presentation. We'll start with a question, talk about how I got my data, how I cleaned the data, some statistical tests and hypothesis testing, and then I'll visualize the results, I'll answer my original question, and then I'll end with some acknowledgments. So the question that we're starting with is, why do some elements whisker while others do not whisker? And so if you don't know what a whisker is, they're small crystalline filaments that grow from metals like this right here, you can see in the picture. And they cause problems. Specifically, they can short circuits in microelectronics, which a lot of devices today have really compact circuit boards. And these whiskers can grow from the solder and short a circuit and cause a lot of damage and cost you a lot of money if you own that equipment. And the photo credit here goes to Dr. Whisker. This is a picture of a tin whisker, but tin is not the only metal that whiskers. So, getting the data. Obviously, this summer we weren't in the lab, so I explored some data available online. I used our package called Periodic Table, and it includes chemical properties of the elements. And luckily for us, we live in the information age, so there's lots of resources available if you can't be in the lab. So cleaning a data frame by combining a column named Whisker with levels yes, no for whiskering ability. There are 18 elements that are known to whisker. There possibly could be more. I had to delete a dummy row. Dummy row 0, there was no number 0 element. Remove higher number elements because of lots of missing data. Atomic numbers 85 through 117. So we're going to be only analyzing hydrogen, atomic number 1 through polonium, atomic number 84. It would have been nice to look at atomic numbers 85 and 117 also, but the thing about the higher number elements is there's just not that much data available on them. It's kind of sparse, not as many people study the higher number elements, and they're dangerous and heavy, and so we're just studying atomic numbers 1 through 84. So I had to remove some columns with some unnecessary redundant variables, symbol, name, the colors red, green, and blue, who discovered it, the year, the configuration, the row, and the column. I wanted to keep configuration in there, but it's kind of a strange variable to study. It's neither like numerical or categorical. It's kind of weird. So I left it out. So several numeric columns have just a couple of missing values. So I had to fill those empty values with the mean value. So these columns included electronegativity, heat capacity, melting point, and ionic radii. We don't have every single data point on every single element. Some things just haven't been measured, but that's okay. When analyzing the full distribution, we can just fill in these missing values with the mean. It's kind of like a band-aid, so you can get a understanding of the distribution without having to scrap the whole project. So another thing I had to do was change the character variables to factor variables. These included type, phase, crystal, whisker, just so you can analyze them statistically. And so some statistical tests and testing hypothesis. So the two tests that I used were t-tests for the numeric variables versus whisker, which is a categorical variable, and then chi-squared test for the categorical variables versus the categorical variable whisker. And I originally started off wanting to just do a linear regression of all the variables with whisker as a, the output variable, but that was just way too noisy of a model and it's hard to understand what's going on. So I just decided the best way to understand what was going on is just test each variable individually. And I think that is the best way to get a clear picture on what's going on. And so in the next slides, I'll include some of the sum of the statistical tests, or at least the ones I found interesting. So yeah, the significant results. Here's a chi-square test I did on the type of element versus the whisker. And the p-value was less than 0.05, so we can reject the null hypothesis. Therefore, the two variables relate to each other. We don't know exactly how they relate, but the type of element matters when it comes to its whiskering ability. And we'll see a visualization of that later on in the presentation. So I did another chi-square test on the crystal phase of the element. And we see as the p-value is 0.07806 greater than 0.05, we do not reject the null hypothesis, therefore the variables are independent. However, the p-value is less than 0.1, so it's still an interesting variable. Obviously, the p-value is arbitrary, but 0.05 is the standard, but generally you can still include data where the p-value is less than 0.1. So we'll still make a graph of it and look at that variable. So another t-test I did was electronegativity versus whisker ability. Is there a significant difference between the means of the numerical variable electronegativity and the two different categories of the categorical variable whisker? As the p-value is 0.05151 is greater than 0.05, that means the difference between the mean electronegativity for no whisker and the mean electronegativity for yes whisker is insignificant. But just as before, however, the p-value is less than 0.1, so it's still an interesting variable. We're not going to throw it away. And so here's a t-test I did on density versus whisker. Is there a significant difference between the means of the numerical variable density and the two different categories of the categorical variable whisker? P-value of 0.03329 less than 0.05 means that the difference between the mean density for no whisker and the mean density for yes whisker is significant. So we'll look at that. We'll visualize that in another slide. So visualizing results, here is a graph of the crystalline phases and whisker ability. So the abbreviations down on the x-axis are BCC is body-centered cubic, CUB is cubic, FCC is face-centered cubic, obviously gas is gas, orth is orthorhombic, and rho is rhombohedral, tet is tetragonal, and Na is not applicable. Not every element has a crystalline phase. So we can see, and I guess it's a green-blue, the elements that whisker in their crystalline phase, and then the elements that don't whisker in their crystalline phase. And it seems that FCC, face-centered cubic, is the most popular crystalline phase for whiskering metals. And then some of the crystalline phases that don't whisker are regular cubic and orthorhombic. I think this is a pretty interesting graph. And for if you don't know, crystalline phases is just how the atoms arrange themselves in a solid state. Like, how do they stack onto each other? And so I found this interesting, and I think this would be a really good area of future research, why some of the whiskering elements prefer certain crystalline phases over other crystalline phases. It's very interesting. So here's another graph of the type of element by whiskerability. I think it's pretty informative. So our transition metal, the type of element transition metal, is the most popular for whiskering. And other types of elements that whisker are metalloids, just regular metals, and alkaline earth metals. So that's important, and looking at the whole grand scheme of the periodic table and what elements whisker and what elements don't whisker. This shows a pretty good picture of, ways to categorize that. And so here is a whiskerability by electronegativity box plot distribution. And so we have the whiskerability on the x-axis, electronegativity on the y-axis, and we have two corresponding box and whisker plots which show the min-max, and then the middle rectangle is the middle 50% of the observations, and then these two black dots up in the top left-hand corner, those are outliers. So you exclude the outliers from the distribution. And so we can see that the median distribution the median value, which is this black line for the elements that whisker, is higher than the median value for elements that don't whisker. And also, as before in the t-test, we showed there was a somewhat significant difference in the means. And this makes sense because the metals, obviously the elements that whisker are metals, and so they're going to have a higher electronegativity. And it's just something to remember about elements that whisker. They're electronegative. So here's another graph. It's a whiskerability by a box plot distribution of density. And we have whiskerability on our x-axis and density on our y-axis. And density is in grams of centimeters cubed. And clearly the elements that whisker are a lot more dense than the elements that don't whisker. And that might seem, that's very intuitive because the Elements of whisker are, metals, but there are there are metals that don't whisker too. So it's just it's an important variable when it comes to whisker. And I think it's pretty interesting. And it makes sense too. A lot of the professional science out there that talks about whiskering, they're always talking about stress in the metal and how that can induce whiskering. And, obviously if a metal is under stress, it's going to be more dense than if it's not under stress. So density matters. And so in answer to our original question, remember the question, why do some elements whisker while others do not whisker? And our answer is, we do not know for certain. We do know that elements that whisker are denser and more electronegative than elements that don't whisker. We also know that whiskering is only seen in transition metals, metalloids, and alkaline earth metals. Also, whiskering is only seen in crystalline phases, BCC, which is body-centered cubic, FCC, which is face-centered cubic, hex, which is hexagonal, rho, which is rhombohedral, and tet, which is tetragonal. And so those are our conclusions. And so I would like to acknowledge Dr. Rodeker, Presbyterian College, and S.E. Embry. Thank you for your support. And I hope you have all of y'all that are watching, have a good time enjoying the other presentations. And thank you for listening to my presentation. Have a good day. Bye.